Hello class, this is Mrs. Jury and we are looking at chapter 13, lesson 1. Okay, so this is going to continue to build on what we did in chapter 12, so they should work well together. So we have a circle, okay, and we're going to talk about circles in relation to polygons, like of course triangles, because it all comes back to triangles. Okay, so I have this circle and I'm going to draw a chord. You can see y'all are going to actually like this better than me drawing on the board because I can use proper tools. Okay, so we have a chord. And if you remember when we were looking at chapter 12, we said that the perpendicular bisector of a chord is its what? Diameter. That's right. Good job. Okay. So a diameter, remember, is a chord that goes through the center of the circle. Okay, so here's my circle template. There's the center of my circle. So my diameter goes through the center. I'm going to use the handy dandy markings on here to get this perpendicular to it. Okay, and draw that diameter of the circle, which is just a chord that passes through the center of the circle, and it's going to be the perpendicular bisector of this chord. Okay, so we actually want to draw here multiple chords for this lesson, 3 to be exact. 3 chords because 3 chords are going to make a what? A triangle. Good job. Good job. Okay. I'm going to draw my 3 chords, and this does not have to be an equilateral triangle or anything because this is actually going to work with any triangle. Okay, so I'm going to go to another side of my triangle. Okay. Find a line that my diameter that's perpendicular to my chord. Do another perpendicular bisector. Okay, and then we can do that again with this chord. You can see here, this is 4 centimeters. It's right here at about 2 centimeters. My perpendicular bisector here. You can see when I bisect that chord and draw the line that's perpendicular to it, I'm using these lines to help me make it perpendicular to it. That's also going to go through the center of the circle because the diameter is the perpendicular bisector. Okay. So we have this triangle, which is made up of chords of a circle. And we've said before that a diameter is a perpendicular bisector of a chord of a circle. Okay, we said that back in lesson 1 of chapter 12. Okay, and so since that diameter can be the perpendicular bisector of the chord, okay, then since the diameter contains the center of the circle, that means all of the perpendicular bisectors of the sides of the triangle meet in a common point. So we say that they are concurrent. Remember way back we talked about lines being concurrent. They share a same point. So the perpendicular bisectors of the sides of a triangle are all concurrent. Okay, but that also means that that point they share is the center of the circle. Okay, and so that means that we can, around this triangle, draw a circle. Okay, and the word that we're going to use here is cyclic. So cyclic, a polygon is cyclic if and only if there exists a circle that contains all of its vertices. Okay, you can see all the vertices of this triangle lie on the circle. So the triangle is cyclic. Not all polygons are cyclic. So you cannot just take any polygon and have it actually lie with all of its vertices on the circle. But because of what we've said about perpendicular bisectors here, we can say that about every triangle. So our first theorem here is that every triangle is cyclic. Okay, and that's because of these perpendicular bisectors. The perpendicular bisector is going to contain the diameter. The perpendicular bisector is the diameter, which contains the center of the circle. And so you can go from that center of the circle that you'll find when you draw the perpendicular bisectors, and then use that center to then draw your circle. Okay. A couple of other terms that we have here are inscribe and circumscribe. And we've talked about inscribe before. We'll actually talk about inscribed angles here again in a second. Okay, because we can also use inscribed angles to talk about why every triangle is cyclic. There's usually multiple ways that we can prove these things. Okay, so we can prove it based on these perpendicular bisectors, but we can also prove it based on inscribed angles. Let's just talk about inscribed versus circumscribed. Okay, inscribed, we said last chapter, means written, so that's scribe, written on. Okay, so we said an inscribed angle is going to have its vertex on the circle. It's written on the circle. Okay, so a polygon is inscribed in a circle if and only if each vertex of the polygon lies on the circle. So you can see here, each vertex lies on the circle. So it's really just three inscribed angles all coming together to form this triangle. So the triangle is inscribed on the circle. Okay, we also have the new term here, circumscribed. Okay, so this you can think instead of written on, this is written around. Okay, so the circle is circumscribed about the polygon. So it's written, the circle is written around the polygon. So it is circumscribed around the polygon. Okay, so you can have inscribed written on the circle, circumscribed written around the polygon. And then we'll change that a little bit in lesson 2. Okay, so hang on to those terms. Okay, let's think of this in terms of our inscribed angles again for a second, because I told you this relates very closely to what we just did in chapter 12. That's why we're going to put them all together, 12 and 13. Okay, so remember what we said about inscribed angles. Okay, the inscribed angle is what? Yes, half the measure of the intercepted arc. Okay, so here's my arc, here's my inscribed angle. The measure of this angle is half the measure of the arc. Okay, so our total degrees in my circle is 360, right? Well, total degrees of my triangle is what? We know this one, right? 180. Okay, 180 is half of 360, right? Okay, so if we think about these all together, let's call this A and B and C. Okay, so arc AB, we write it like this, measure of arc AB, okay, plus, we had this arc addition postulate, plus the measure of arc BC, plus the measure of arc CA there, is going to equal 360 degrees, right? That's my whole circle, okay? Each of these angles, so this angle here, angle C, is an inscribed angle, so it is half the measure of AB, right? Okay, so angle C is going to be half the measure of AB, okay? Angle A is half the measure of arc BC, okay? And then angle B here, angle B is half the measure of arc CA. Okay, we know that in a triangle, those add up to 180 degrees. Okay, so if angle C plus angle A plus angle B add up to 180 degrees, okay, the arcs that they intercept add up to twice that, 360 degrees, then we see that these angles are half the measure of their intercepted arcs. Okay, since the measure of a triangle is always going to be 180 degrees, no matter what kind of triangle it is. So we can do this with any kind of triangle. Okay, not a negative triangle, Silas. Okay, you can have lots of different shapes of triangles and they're still going to be inscribed in our circle, okay, because the angle, okay, this angle is half the measure of this arc, this angle is half the measure of this arc, this angle is half the measure of this arc. So we have a small arc, we have a couple of larger arcs, but still all three of our arcs have to add up to 360. All three of our angles have to add up to half that, 180. Okay, that should be everything you need for lesson 1. Okay, and I've shortened down the homework for each of these lessons. So it should be pretty short, but keep this in mind. We're thinking about the inscribed angles here. So go back to what we talked about with inscribed angles in chapter 12. Okay, let me know if you have any questions.